Okay, hello everyone. So welcome to my talk. You already introduced it. So it's about Zoom and their local recordings, how they're stored, and how I reverse engineered all of that stuff. So first, a little bit more about me. I'm currently finishing my bachelor in computer science at ETH. I'm a member of Flagbot since over 2 years now, and I've been the president of Flagbot over a year. So now, what is Flagbot? As you already said, Flagbot is a VIScon committee and also ETH's Capture the Flag team. And as you already alluded to, Capture the Flag or CTFs are team-based cybersecurity competitions that often also involve actual real-world attacks. And in both 2019 and 2020, we were ranked first place in Switzerland. And one of our most recent achievements was fifth place, together with polyglots from EPFL, The Crown, Excuse Me, What the Fuck, and Secret Club in the Zero CTF finals. Now we play CTFs on the weekends, and we also have weekly meetings on Mondays, currently over Zoom, that are open to anyone. So if you're interested in cybersecurity or CTFs, just come and stop by. You'll find more information on our website. You can also write us an email if you are interested. And yeah, during the meetings, we like to discuss challenges and also have some small lectures that are aimed towards beginners. So even if you have almost no knowledge, feel free to join at any time. Great, so with that out of the way, an introduction to this topic. So as a lot of you probably also had to do, or in a similar manner had to do, we had to shift our in-person meetings from, well, in-person to online at the beginning of this year. And I still wanted to upload and record all these lectures we were doing, but one of the big issues I had was the audio mixing, because as you all know, in a Zoom talk, you have the quiet guy, you have the very loud person, you have the one that's just screaming in the microphone, you have the mic that's just really bad. So audio mixing, if everything is on the same audio track, very, very difficult. And luckily, Zoom allows you to export every person as a separate audio file. So that would have been really great. Unfortunately, what they don't tell you about that feature is that they just remove like any period of silence that's longer than a few seconds. So if you see here up top is the audio file as exported by Zoom, and here's what it should actually look like. And you can imagine this is going to be a nightmare to try and synchronize with all the other people. So that was a bit of an unlucky break for me. But then I had an idea. So, I mean, Zoom obviously has to store these somewhere, so I found out that Zoom has these temporary files that are named like double-click to convert 123.zoom. And I thought, well, they probably have some timing information in there, so my goal really was to figure out how these recordings exactly are stored in those files, and then hopefully extract the audio without any stuff removed. And I mean, nice to have would have been that I can also extract some higher quality video, because if you export the video with Zoom, it's pretty terrible quality. And my major approach to this was just reverse engineering the transcode app from Zoom. And the transcode app is the thing that takes these temporary files and makes video and audio for you. And some of the side effects, as I like to call it, is I learned a lot about Zoom's software architecture, actually, and also the H.264 standard, which is just a video codec. So just a quick overview of what I'm going to talk about. I'm going to do some general introduction to reverse engineering, also a bit C++ stuff. Then I will talk about how exactly I went about reverse engineering all this Zoom stuff. And in the end, I'll showcase some of my findings. Now, what are some of the general reversing tactics? Well, we like to talk about these two major approaches, which are static versus dynamic analysis. And usually, you want to use a combination of both. And all of this obviously not just applies for your compiled application. It also applies to JavaScript, to Python, and a lot of other stuff. So, yeah. So what is exactly static analysis? This is really when you look at your application while it's not running, you don't interact with it at all, you just look at it through some external tool without doing anything dynamic. Well, what you usually do is you look at it through a decompiler or a disassembler. And the disassembler is basically, it takes the application, the ones and zeros of your application, and gives you actual, somewhat human-readable machine code, so you don't have to stare at ones and zeros all the time. And it also usually gives some advanced features like it annotates functions and stuff like that. And then you have the decompiler, which takes this disassembly and actually gives you some amount of high-level code. So it's even more human-readable and easier to understand. There's some popular free tools, so if you're interested, at the end there's going to be a few links. And there's, of course, also similar tools to this for non-compiled languages like your Python, your JavaScript, and so on. Now, what we usually do with these decompilers is we figure out what types are in this binary, what the clauses look like, the function signatures, what the function actually do, if they aren't named there, and a lot more. So this is usually enough for simple binaries and small binaries and easy CTF challenges, but it can quickly get very complicated, especially if you have a big software project like Zoom. And in addition, what you also usually do is you analyze the supporting files with other tools. There's, for example, binwalk, which just basically goes through your files and tries to extract anything that's somewhat looks useful. For example, if it finds anything that looks like an image, it will try to extract it and show you. And what is also interesting, which we'll see later, is that often if you just look at stuff in a hex viewer, you can already figure out some patterns and maybe don't even have to use all these fancy tools. So in contrast, we have dynamic analysis, where you try to gain your insight into the application by analyzing the stuff at runtime. Now, often this involves attaching a debugger, running through your application, stepping through functions, analyzing memory contents. Usually, also your static tools like your decompiler have an integrated debugger that also helps you to verify your findings from your static analysis there. So you, for example, you reverse a clause, you check, okay, I think this points to a name somewhere in memory. You load it in the debugger. You look at the memory and see, okay, it shows 20 there. Probably not a name, probably a number. So then what you can also do is you inject code and hook functions. So instead of scripting your debugger, that can sometimes be very painful, you just write your own code and execute that instead of the function of the application. There's also something called symbolic execution, which I'll not go into detail, but if you want to know more, I think it's really cool. I have a link here and at the end. And especially for me, I think this is often underused a lot, so I usually do way too much static analysis in comparison to my dynamic analysis, and this, especially dynamic analysis, is helpful with C++ suite tables, which I'll now go into a bit of detail. So, what are C++ suite tables? Well, first, let's have a simple example. We have a class that's animal, a class that's dog. We have animal is the base class, dog inherits from animal. We have two functions, eat, try pet. Now, eat is just a normal function, only animal implements it actually. And then try pet, well, your normal animal, you don't know whether you can pet it, so let's just say any animal you cannot pet, let's return false. So that's here. But then the dog actually overrides this try pet and says, well, usually you can pet the dog, so let's return true here. Great. Now, how does it work with this eat function? So this is just like it would work in C, or really any compiled language similar to C. The only real thing here the compiler does is it adds this statement, so you can reference back to the class. Not really that important. This also doesn't really have a big impact on reversing, so this is very easy, especially very easy to figure out where this function is called from. And this is very important because you want to figure out, okay, is it here this binary is doing this, then this, then this, so you want to really figure out where all these how all these functions come together. Now, here we have an issue. So we have another function here. It takes an animal, and if it can't pet the animal, then it will print an error message. Now, obviously, if you pass in a dog, we don't want this error message here because, yeah, we can pet a dog. The problem is, how can the compiler know which try pet to call? We have two implementations. One of them returns false, one of them returns true. So which one do we actually want to call? And to solve this, we use something called virtual function tables, or vtables for short, that enable this dynamic dispatch. So sounds a bit abstract. Let's look at it. This is how the animal class would be laid out in memory. So first you have a pointer to this virtual function table, and then you would have other properties here like hunger, food, etc. And then you have this virtual function table. So here this basically just has a pointer to the actual implementation of try pet. So for any dog, this vtable here would have a pointer to the implementation that returns true. For an animal, this would have a pointer to an implementation that returns false. And then in the end, the compiler, when you type this in your code editor, dog try pet, the compiler will instead then do this, so dog vtable try pet. And here it will then have the correct try pet function, and we can actually pet our dog. However, this has some disadvantages, well, at least for us, namely that it's much harder to reverse, because with this, you can't just easily look up, oh, this function is called from here. You have to then figure out, okay, this is a V table, okay, where is it used, stuff like that. It's not at all trivial to then figure all this stuff out on how these functions interact. So, with that out of the way, let's talk a bit about the process I took reverse engineering the Zoom transcoder. So, first, a general overview. I used, obviously, both dynamic and static analysis, and especially in the end, I frequently switched between them. In the beginning, I didn't really use dynamic that much, and we'll see what that did later. And so I also used my decompiler and text viewer quite a lot, and I reconstructed many of the class hierarchies you find in the binaries myself in the decompiler, and then I also used the debugger to then verify these class hierarchies, as I explained before. I also verified my findings with Python script, so if I figured out, oh, okay, this thing in the file does this, then I used the Python script to extract all these things from the files and then verify, well, is this actually true? And I also, as I explained, used the debugger and binary hooking for verifying the class hierarchies. And sometimes even educated guesses were enough. So for example, you have the 3 files, as I explained before. One of them is a lot larger than the others, and then I said, well, probably that contains the video data, and that's correct. So sometimes you can just guess a bit, and you're probably right. Now, how did I start all this? Well, at first, I opened my decompiler, opened transcoded app, and it was suspiciously small for a main application. So I was a bit suspicious, and unfortunately I was unable to find the actual file names anywhere in there. So here you see some strings, and these were some interesting logs I found, but none of the actual file names, so double-click to convert was not in there somewhere, which is unfortunate. And then through some more static analysis, I quickly figured out that the actual work is delegated to this other library called MCM. And I opened that one up as well, and it's very opaque. So you have almost no exports, imports, or symbols. So symbols you can think of as just function names. So if you have no symbols, that just means all the functions have names like sub 1234, sub 12345, and so on. So not really a good thing for reversing. And exports are just symbols that you export so that are symbols that other libraries can call or other libraries can use. And imports are stuff you use from other libraries. And these are usually where you start your reversing process, because if it reads files, usually those functions are implemented somewhere else, so you actually import them. And if you don't find any imports for file functions, well, good luck finding anything to do with files, or, well, you just have to figure out what else they are doing. So that was kind of a bummer. And I did a lot of static analysis, and then after some time, well, I finally did some dynamic analysis, and I had great success. So I started the transcode app under the debugger and just pressed pause in the middle of the process, and I was hoping that the call stack will reveal some good information. And at first, the call stack looked very bare bones, and I was like scared that I was going nowhere, but I figured out that there was a lot of threads, so I switched to a different thread. It had this call stack here, which was very interesting because you have the video deck, which probably stands for video decoding, and file source, which probably stands for the temporary files I was talking about earlier. So I finally figured out where I should start. You can see here that says setMB, so I should probably look at the setMB library. So I opened the setMB library, and although it looked promising before, I mean, could be heavily obfuscated, could have no symbols again, so I was a bit skeptical still, but luckily, most of the functions fully retained their names along with their argument types, so that was very good. I had a lot easier time reversing this than I initially thought. However, there is still heavy use of C++ throughout the binary, so figuring out how all these functions interact was still a great pain. And then I also finally found the file names. So here you see in this library, I finally found the file names I was looking for. So I looked where those are located, and I started reversing backwards from there. And so here I have a small example of what this looks like. So this is at the very beginning still. Here we're reversing a function that reads the file header. So this looks very, very unusable, basically, because you have a lot of variables that are initialized, all different names, these offsets, stuff like that. You basically have no idea what's going on. So you start reversing smaller and smaller functions, so you can then work backwards, so you have the bigger picture. And here, this is after a lot of annotation, cleanup, and stuff like that. So here we see all these variables that were previously different variables are actually one big thing I figured out. We have this stuff, I figured out it's this version and stuff like that. And all this looks a lot better. So, and then we can clean out the error, the parts that check for errors and stuff like that, and then it's even a lot easier to read. So here we see what it does. It first initializes a buffer of 96 bytes. Then we have this version here thing. This is just initializing it in case it doesn't read enough data. Then here we read this 96 bytes from the file into this array. We set the version info to this, which is the version info. You can also just ignore it, just for Zoom internally use, basically. Then we check that the first 8 bytes of the file are actually this, so this is just verifies that it's actually this temporary file format and not just some other random file. And then what's also interesting is we look at this offset here in the file, and this is basically tells Zoom, okay, downwards in the file at this offset, the actual interesting bit starts. So go start looking there now. Now some further investigation was needed. And I started from the previous function, of course. I worked my way backwards, and I restored some class hierarchies in the binary and found locations where these file contents are actually used. I quickly located then from there functions that are relevant for parsing the files. However, they only do some very basic parsing, so they basically split up the file into packets. And this wasn't that useful because I couldn't figure out from there directly what the actual contents of those packets were. And also, as I said before, often with just a look in a hex viewer, you can already figure out quite a lot, because if you look at it in a hex viewer, this splitting of packets is quite obvious already. So I started reversing even more, and then time by time, a lot of the fields actually became apparent, and I figured out what they do. So for example, there's timing information, there's extra data size, there's type, and so on. I will talk more about that later. And this also allowed me to differentiate between different types of packets, so I was able to actually start with my next goal, which is extracting audio. So I extracted all the audio data, and the question now is, well, what format is it stored in? Is it just your MP4 or whatever? So I concatenated all the audio data, dropped it into Audacity. It said, well, unknown format, please try again. I was like, okay. I tried importing it as raw audio, and then I had to set some parameters, and I set it to 8-bit PCM stereo, and this is the result. I need to do this. So, not that great, I must say. But I don't know if you heard it, but the one side has a very different sound than the other, and you actually can hear something like my voice probably on one of the channels. And so I was like, okay, so maybe it's actually mono. And I also looked at the output that the transcode app gives me, and it was indeed mono. It was also, it's at 32 kilohertz sample rate. So I changed it to that, imported it again, and well, it actually sounds worse than before. So I was like, okay. But then I realized, well, the length is exactly double that of what it should be according to the transcode app's output. So I thought, okay, well, I need to double or half something. So I tried doubling the bit depth. So I did 16-bit PCM mono, and now we can actually get the correct output. Yeah. To go back, yes. This is a test recording. So there we have audio extracted. Now, one thing I still had to conquer was that, of course, I wanted to know which person actually spoke the audio. So I also saw that every audio packet had a name attached, well, a name identifier, I must say. So just a number. It was actually kind of consistent across meetings, but I still didn't know how that related to the actual username of the person. So I spent a lot of time reversing maps and stuff like that in the binary, basically a waste of my time, because I just ran the second file through a hex viewer, so, oh, this is my name here. Oh, it's next to the number I was looking for. Great. And since the file also follows the same, well, not exactly the same, but similar packet format, I was quickly able to actually get the useful mapping out of this. And I also guessed some fields of those packets, and that worked out well. Now, what about video? I was talking in the beginning about video, and this proved to be quite a bit of a challenge. So I looked at the video data in a hex viewer again, and this time I did that first, which proved to be quite useful because I quickly saw these 4 bytes here, which are NALU start code prefixes, which basically just means it's H.264 or H.265, if you don't know anything about that, but it just allowed me to quickly identify the video codec format. Now, I tried running it through FFmpeg. Well, as you see, maybe not the best result. I don't remember having this on my screen while recording the test, but oh well. Yeah, as you see, it didn't really work out. So I was like, okay, let's start reversing again. And the SAT-LT framework is actually responsible for all the video decoding. I looked at it, and it is like full of virtual method calls. It has over 400 classes, almost no symbols, no exports or imports, and some preliminary dynamic analysis basically revealed nothing of interest, except that, well, it's probably H.264, but some other stuff added, I guess, because it didn't work with FFmpeg. And here you see an example of a C++ class I reversed there, which, yeah. And you had like 400 of those, so you can imagine that's going to take quite a long time, and yeah, going to be a bit of a pain. And here you also have another example of how this would look like in the binary, how these virtual method calls, you see this pointer is dereferenced like 3 times. That's already really annoying, and you have all these different things that you don't really understand, that this is just one function out of like 5,000 or so good luck. Well, then I thought to myself, okay, this seems a bit annoying. I started reading the H.264 specification. I was like, okay, this is very difficult to understand. 700 pages of just boring specifications is not really that great. I also looked at FFmpeg's implementation. Maybe there's a bug there or something they do very different. Doesn't have any comments, not really easy to follow or understand. Also, I don't think it really follows the specs that closely, which is interesting. So I thought to myself, well, debugging and changing FFmpeg would be difficult. Or so I thought, at least. And I had an idea, well, let's just build our own decoder made for debugging and fixing all the zoom stuff. That should be easy, right? So, no. Let me tell you, don't do that. This is a really bad idea. Even just parsing H.264 is extremely complicated. And by parsing, I mean you don't even try to decode the actual video. You just want to figure out what the stuff in the file means. And that's just still so complicated because there's a lot of weird stuff going on. There's so much intricacy to this that if you just do one function wrongly, well, have fun figuring out where that is, because all the other functions will also give you a wrong output. So really not a great idea. So I went back to SAT-LT, took another look at it, especially now that I'm armed with a lot more knowledge on how an actual H.264 decoder works and how it would be implemented. And I also concurrently looked at FFmpeg a bit more, figured out a bit more about that implementation. So I managed to actually reverse engineer quite a lot of their code, even though at first, again, I relied way too much on static analysis. Using a debugger then helped me quickly identify how the C++ classes interact, how their methods are called, where they're initialized, and so on. And I also found a few interesting things while poking around in there, but I will get to that in a bit. And yeah, the unfortunate thing though is I, at that point, figured out that the video stored there is already in the pretty bad quality you get when exporting it, so this whole effort proved a bit pointless. So that's why this image is here, but yes. Now, on to the findings. What did I find out? Well, first about these files. So onto the basic file layout. So first, again, as I explained before, we have this file header which contains the information like your version and offset to the actual important bits you want to figure out. And then you have this data part where the offset points to. And this is, again, split into many small packets. And these are delimited by this header, so these 4 bytes, and this trailer, these 4 bytes. So as you can see here, for all files I found, it starts at hex 400. And there you first have these header bytes. So this says, okay, here is the first packet. Then these 4 bytes in red are the type. The white ones are usually not important / unused. Then we have these green 4 bytes say how much data is in this packet. So here we have 0 data. This says something about the properties. For example, for video, the property would tell you the width and height of your video. For audio, you would have the name identifier in there, and so on. Then again, just unused stuff. Then here is the trailer, so this says, okay, the packet is now finished. Here we have, again, a new header, so this says, okay, now we have the next packet. We have the type again. Then we have useless stuff, useless stuff. Here we have the data size, so this is actually quite a large packet, has a lot of data. Here we have the property size, so this has also properties, so here's some information about the packet, and then we have the actual data, which here is just 000 because it's at the very beginning, and this is audio data, so you don't actually get, in the beginning I was muted, so you don't have any actual audio data, so that's why there's zeros there. Great, and so again, coming back to the purposes of these 3 files, because why are there 3 files? I mean, couldn't they just have made 1? Well, the first file contains your screen share, your webcam, avatar, and cursor packets. The second file contains something they call command packets in code, and this is stuff like, a user connected to the meeting, a user disconnected from the meeting, started screen sharing, or also, again, the usernames and how they map to the name identifiers. And the last one is the one I'm actually interested in for this, or is this contains all the audio sample packets from the different people. Now, just bit here. So we have the cursor is actually kind of interesting because it stores a bitmap image file of your current cursor alongside the screen position. So every time you move your cursor in Zoom and someone is recording, it sends an image of the cursor along with its coordinates. Well, just if you're also screen sharing, not if you're just in the call. But yes, it's still kind of interesting that they do it this way. For the avatar, it just stores again, an image of the avatar. And if you're interested in more in-depth stuff, there is, at the end, again, a GitHub link where I have a library for extracting all of this data and stuff. And yeah, also documentation is coming, but there's some documentation there. Now, finally, some other interesting bits and pieces I found. So one thing regarding the software architecture is that it's organized in an extremely modular way, right? You have all these different frameworks that have different purposes and call each other, but some parts of it seems kind of unnecessary. For example, you have the MCM framework, which just calls another library again. Like, the only really thing it does is it initializes a class from another library, so why is it even there in the first place? And also, all the exported C++ classes that are used in like this cross way between libraries, they have C wrappers, which you usually do if you want to have greater compatibility between libraries and languages as well, but they just use the C wrappers for initialization, and then afterwards they still use the C++ function. So I don't know, maybe they gave up halfway through, or they didn't really understand what they were doing, I don't know, but it seems interesting to say the least. And also ZMB uses a pipeline architecture. So every operations it does on the recording files, so for example, reading them, converting them, writing them to disk is basically a node in a graph, and then it runs through this graph, and nodes communicate between each other. It doesn't seem to be really that useful. I think it probably has a lot more overhead than it actually saves, because except for the actual multiple audio files per person, for every person you have one audio file, you don't really have a wide graph, so there's not really much parallel processing going on. So here is this pipeline visualized. So this thing here, this whole thing would be here for every person, but there isn't enough space on here. So yeah, you read in the file, you give it to source audio file, this node, this then for every person creates a new subgraph here, and then runs it through here. And then lastly, so the transcoding engine, which I spent a lot of time reversing, which in the end, again, pointless, but oh well. We have it here. So CLT, SATLT seems to implement their own version of an H.264 encoder/decoder. I don't know why, they just do. I definitely found one small bug in there. You have this, instead of actually doing writing 1 bit into the output file, they write 3 bits in one of the headers. This basically leads to a reserved 0 bit being set to 1, and you don't want the reserved 0 bit to be 1. So this is your first hurdle when you try to decode the H.264 in a different program, because FFmpeg is like, this shouldn't be 1. I'm stopping now. Yeah, there's also a Boolean flag that basically just enables or disables certain functions which do completely different things than the spec suggests you should be doing, which I find very weird. So if you want to have actual H.264, you can disable the switch by selecting optimize screen share for a video clip, and then basically you have normal H.264. And of course, this also made reversing and actually figuring out what is going on here very, very difficult. And finally, what I also found interesting is that I found a fully functional hardware decoder inside this library. It was not used, though. The code was there, it was never referenced, though, which is interesting, but makes sense in the way that it's likely not used because of it's, again, the output is not spec compliant, so you can't really use a hardware decoder. And this is kind of unfortunate because it would probably speed up the decoding and transcoding process by quite a lot. So yeah. Well, I'm now at the end of my talk here, so here are the useful links I promised. You will also probably find these slides on our website. Well, you will find the slides on the website because these links have a bit more to it, but didn't fit on a slide, so click on them in the slides if you would like to know more. So thank you very much for your attention, and if you have any questions, well, now you can ask them.
All right, now comes the fun part, the questions. If you have questions at home, again, you can send them at our link in the description below to the Blue Room, and a helper will read them out loud. And for you, I have the microphone, I will come by, and don't worry, I will disinfect everything for you. So if you have questions, feel free to ask them.
Do you have a rough estimate how much time you needed to do all of this?
Well, I would like to say it's below 1,000 hours. It's probably in the range of 500 hours spent in total, I would say. I think that's a reasonable estimate.
All right, maybe also a question from my side. Did you also share those findings with somebody actually working from the Zoom company or not?
No, not yet. I don't think they will be very much interested in this, but I will definitely try and contact them, especially about the box, well, one of the bugs I found, so.
So the question was, what was your motivation to do that?
Well, in the beginning, it was really about trying to make the audio mixing work, and by I don't know, some point at like 100 hours probably, it was just, well, I started this, now I have to finish it, and I don't know, it was also kind of fun learning all these tricks in reversing, improving my reversing knowledge, trying to figure out how I can improve all of this. I can make reversing, especially C++, easier, because it's a lot harder than your normal application. So if you want to have a secure application, just write it in C++. It's going to be way harder for me to reverse.
What are the outcomes in software out of this? Do you have a software tool you use for the audio mixing now?
Yeah, so there's the GitHub link here, which there's, well, at the moment you have to compile it yourself, but it's a tool that you can use for extracting the audio and actually also the video data from those files. So yeah, the audio mixing I was still just doing in video editing software in the end, but I at least had all the tracks separately.
All right, if there are no more spontaneous questions, I guess you can still send them to Leo at...
Yes. Well, this is at the very beginning, so let's see. Quickly, I can go back. Yes, so if you select local recording during a Zoom meeting, they will appear on your hard disk. Well, if you want to use them, I recommend turning on the setting keep temporary recording files, otherwise they vanish the moment the transcode process finished. But yes, if you, I'm not sure, I think you can also, depending on the settings, you can also record if you're not a host. So if you just say record on locally on this computer, it should generate those files.
All right, our time is nearly up for this talk. Again, if you like to ask more questions, you can write them at Leonardo directly, at leonardogalli@vis.eth.ca.